Fantastic. Well, thank you so much for joining again for another HRAI webinar. This time we are joined once again by Phil Boudreau with Bitzer. He's been on here a bunch of times with some fantastic information, and this time he's going to be taking kind of a deep dive into operating envelopes with a focus on reciprocating compressors. And at this point, I will ask the man himself to turn on his camera and say hello.
Good morning, good afternoon.
There he is, coming in loud and clear. Before we begin, just a few housekeeping items that you might have heard if you joined us earlier. But we will be taking questions at the end of the presentation. You can put those into the Q&A button at the bottom of your screen or the chat function too, and we will monitor and collect them and get to as many as we can before the end of the webinar. Also, this is being recorded, so you can enjoy it again or share it just by going to HRAI's YouTube page. And with that, I'm going to turn it over to the musical guitar man himself to get us started.
At one point in time.
At one point. Thanks so much, Phil. After you.
Thank you very much. And again, everyone, welcome to the webinar. Good afternoon, good morning. As Matthew mentioned, we're going to cover operating envelopes specifically for reciprocating compressors. I was actually going to cover, I thought I'd throw in screw compressors and schools and found out that the presentation would simply be too long. So perhaps it's, a topic these are other topics we can cover at another point. So moving into the presentation, on the agenda, we have exploring the envelope. So this is the various sections of the envelope and what they mean, what are the various limits represent, and what happens if we cross those limits and that sort of thing. Low and high pressure controls, basically one means of keeping compressors inside envelopes. Unloading limits for compressors. We'll also talk about the speed limits, various speed limits of reciprocating compressors. Minimum superheat requirements, which is a topic I cover a lot in many webinars, very important topic, especially as we get into refrigerant CO2 or R744A, or R744 rather, sorry. Limiting suction pressure, how do we do that? Okay, it's another form of keeping compressors operating in the envelope. And then auxiliary cooling and the methods of auxiliary cooling and how they're controlled. And then we'll get into discharge temperature monitoring and some of the pitfalls of operating compressors at high discharge temperatures and what we can expect to occur when that happens. So to get things rolling, we'll take a look at a basic envelope for a compressor. Okay, so along the horizontal or the x-axis or the abyssa, we have the saturated suction temperature. Sometimes this is referred to as evaporating temperature, but note that your saturated suction temperature really is oftentimes, well, it always in theory going to be less than your evaporating temperature. And when we refer to limits for a compressor, we're considering what's going on or what the compressor sees. So the actual suction conditions and your discharge conditions. So on the vertical or the y-axis, or otherwise called the ordinate, we have saturated discharge temperature. So this, with the envelope, we can see the operating range or sandbox that a particular compressor can operate in. Additionally, we'll have different motor sizes. So for a given displacement, there is generally more than one motor. Okay, so this will depend on the application. It'll depend on the refrigerant type. First, we have a motor 1 here, and then we'll have motor 2 in this particular envelope. So motor 1 is larger. Note that it can operate at higher saturated suction temperatures and also higher saturated discharge temperatures, because of course operating at these higher pressure conditions requires more work, so we need a stronger motor. So the capacities between the motor 1 and motor 2 are similar, but we need to have enough motor to get the job done, of course. And in some cases we'll see, in fact, a motor 3. Okay, so this would be basically the smallest motor for a given displacement. As an example, 134A, oftentimes you'll see 3 motors. So depending on where you are in the envelope, that will determine what you need for motor. And the other thing is too, if you select for a motor 2, okay, you can your maximum saturated suction temperature in this particular case is approximately 55 degrees Fahrenheit or so. But in that same application, you could actually select a motor 1, and now you've got more horsepower to pull the suction pressure down. So, you know, this is something that could be done in like a blast chilling process, for example. This area here to the left, it's highlighted in yellow, is your area for what we call it thermal limits. So this is where auxiliary cooling and or limited suction return gas or superheat has to be considered. The higher the return gas superheat and return gas temperature, the higher the discharge temperature for a given application. This area down here, so you can see it's highlighted in green, shaded green here. This area is established. So this is basically your minimum pressure ratio area here. So the minimum acceptable forces on reeds, for example, reeds need to seal up properly to be efficient. This also has to do with the effectiveness of the lubrication system. Okay, so when you're operating low pressure ratios, this actually will have it can have a negative impact on the lubrication system if we take it too far. Some of the effects of this, with low compression ratio, like I said, reed valve leakage, which leads to valve leakage, reduction in efficiency. With the higher mass flow rates that will exist at low pressure ratios, we can also expect that the reed valves are going to be working very hard. And when you operate compressors outside the envelope and there's a lot of very dense high pressure refrigerant coming back, we can experience, the reed valves can experience breakage, deformation, that sort of thing. And of course, reed valve breakage can result in other mechanical problems, depending on where those reed valves end up. Low discharge superheat is another one. So heat of compression comes from, of course, compressing the refrigerant. The lower the compression ratio, the lower the discharge temperature. And as you may know, Bitzer does specify minimum discharge superheats. And the minimum discharge superheat is really a way of controlling the amount of refrigerant that's in the oil. Because the more refrigerant we have in the oil, the more we're diluting it down and reducing its viscosity. And if we reduce the viscosity too much, then of course, there's insufficient lubrication for the compressor. So, and in this case also, it does tend to contribute to higher oil carryover rate, especially when the oil foams up on you and now you've got a crankcase full of foam. A lot of that foam is just going to get pumped out into the system. And sometimes this is mistaken for a compressor problem when in fact it's a lubrication problem. The maximum, this area here, which is your maximum saturated suction temperature, this is established by the highest forces permitted on the drive gear. And the effects of this are increased stress and wear on the bearings and the pistons, the wrist pin, for example. This area up here, so this is our motor 1 area. You may recall this line here indicates, these two lines indicate the limits for the motor 2. So for motor 1, this is your maximum saturated suction temperature. This is your maximum saturated discharge temperature. This is basically the most we can expect to get out of the compressor in terms of its maximum pressures. Okay, so if you exceed those values, there's a very good chance that it's likely that the compressor will overload. And if this happens for long periods of time, this will eventually lead to motor burnout. And unfortunately, with motor burnouts, as you may know, this can also result in an acid condition throughout the system. And then acid really needs to be dealt with carefully because future compressor replacements, they can have a short life if the acid is not totally cleaned up. So with the motor 2 limit, of course, this is limited even further because this is a smaller motor. So it can only withstand pressures of saturated suction, saturated discharge pressures or temperatures rather, that are somewhat lower than the motor 1 version. So you can see here on the right, it says 4PE dash 15 and 12. So the P basically indicates the displacement code for this particular compressor. It's a 4-cylinder with a P displacement, just a letter to indicate a certain displacement. E for equal line, and the S is just for the non-oil pump versions. So there's oil pump versions, non-oil pump versions. Then you have, we'll call this a nominal 15 horsepower and a nominal 12 horsepower. So as you can see, the 15 would be your motor 1 compressor, which can operate the entire envelope. And then the nominal 12 would be limited to this area here. This area at the top is established by our maximum. This is our maximum allowable operating pressure of the compressor. And another limitation here are lubrication limits. The higher the temperatures, the lubrication can become an issue. You know, aside from having too much refrigerant in the oil and reducing viscosity, of course, when you increase the temperature of an oil, it will reduce its viscosity as well. And then this area, as I mentioned before, this is established by the compressor thermal limits. So effects of this would be motor overheating, high discharge temperatures, lubricant failures. And this is where we get into areas where we have to really consider the head cooling fan or auxiliary cooling options, such as a head cooling fan, liquid injection, even limiting the suction gas superheat. So in this example, keep the superheat less than 35-degree Rankine, or the return gas, keep that less than 40 degrees Fahrenheit. So, and then in some envelopes, you'll see more than one shaded area. There could be 2 or 3, and then you just go to the legend and see what each shaded area indicates. So they get progressively more limiting, okay, as you get up towards the upper left of the operating envelope. And this area down here, this is established by, so this is your minimum allowable saturated suction temperature. And this will be like all areas of the envelope, in fact, dependent on the specific compressor, but also the refrigerant type. As you know, lower refrigerant pressures, or lower pressure refrigerants rather, such as R134A, 513, 450A, and there's a host of them. These, because they're fairly low pressure, we can run into a vacuum sooner with those particular refrigerants. So we do have to be aware of this particular area. We don't want to operate a single stage semi-hermetic compressor in a vacuum, because in the event of a leak, obviously we're going to be bringing air into the system then, resulting in non-condensables that tend to hang out in the high side. And this area here is established by our low discharge gas temperature. So specifically, we're talking about the minimum saturated discharge temp, or you loosely call it the minimum condensing temperature, this area here. You may recall this is the condensing axis here, or the saturated discharge. Okay, so this is your minimum and this is your maximum. And the maximum actually drops off as the evaporating temperature drops off. And the minimum saturated discharge temperature is down at this low level here, but is allowed to increase with progressively increasing evaporator or SSTs. Low and high pressure controls, of course, we should never have these controls allow the compressor to operate outside the envelope. Okay, so we never want to set a low pressure control to a value that will allow the suction pressure to drop below the minimum design saturated suction temperature of the compressor. Similarly, never set the high pressure control to a value that will allow the discharge pressure to increase above the maximum design saturated discharge temperature for the compressor and for the specific refrigerant involved. And this is very important, that these pressure controls are set correctly, and it is ensured that they cut out at the correct points, because these are very important ways of keeping the compressor operating inside the envelope. For the actual port locations, you can refer to the drawing for the compressor. So in this case, we have 6-cylinder compressor. This is a range of 6-cylinder compressors here. And you'll note that there's a low pressure port shown here. And in the case of the high pressure, there's actually 2 ports showing. So in order to determine which is the correct port to actually connect something to, we would look at the legend here, and you can see that, well, for a single stage compressor, port number 1 is for the high pressure connection. Okay, so that would be here, your high pressure control. Port number 2 would be for your discharge temperature sensor. Okay, so that's how we know where to put them. We just refer back to the legend, and then we know. And these port locations are available for, again, for single stage, 2-stage, just as they are with all compressors, the screws and the scroll compressor series. Unloading is another thing. So with the IQ module and VariStep, the VariStep algorithm that's integrated with the IQ module, this allows us to operate a compressor in theory down to 10%. But just because we can operate a compressor down to 10% doesn't mean we should. And the good thing about the IQ module is it's going to limit how much the compressor can unload anyways. But if you're using fixed step unloaders, we do need to be aware of the fact that there are unloading limits depending on compression ratio. So again, the further we get towards the area of thermal limits, the less we can unload. You can see that this line here indicates once we cross that line, we're into an area where we cannot unload any more than 20%. Okay, and then in this case over here, the limitation is 33%. Okay, if we're out in this area, we can actually unload all the way down to 10%. And you'll notice that there are, as I mentioned before, there may be a picture of a fan icon here, or other limitations such as return gas superheat, return gas temperature. It's very important that we are aware of these things on the envelope so we can make sure that the compressors are protected accordingly. Oftentimes, compressors fail due to lubrication issues, operating outside their envelope, superheat issues, things like that. Sometimes there's electrical issues, of course, as well. Voltage is too low, voltage spikes can create problems for compressors, of course, as well. So with the IQ module, really this is the best, this is really the only way to control, in my view, the unloaders when we're using a VariStep control. So when we're trying to pulse the unloaders, the algorithm that's used in the IQ module does this safely while respecting the envelope of the for that compressor and for the particular refrigerant that are used, and also depending on the saturated suction temperature and pressure, saturated discharge temperature rather, that the compressor is operating at, and it's also looking at the discharge temperature as well. So if the compressor starts to, if it's getting pushed outside the envelope, then the IQ module is automatically going to back off in order to protect the compressor. So if you're just applying pressure controls, you don't have that ability to pressure controls themselves don't have this ability. The IQ module can do it. So you'd have to be very careful when you're unloading compressors using fixed step unloading. Envelopes sometimes include speed limits. Sometimes they're just published this way. It'll be in a table or something like that. For example, in terms of the reciprocating compressors, HFC compressors, 2-cylinder, the general range is 30 to 60 hertz with the possibility of going to 70 hertz. 4 to 6-cylinder would be 25 hertz to 60 hertz. Again, with the possibility going 70 hertz. And then with R744, otherwise known as CO2, the 2-cylinder, 30 to 60 again, and then 25 to 60 for the 4 to 6-cylinder compressors, with the possibility of overspeeding as well. But note that overspeeding, as you speed up a motor, you're doing more work, or the motor's doing more work. And we run into we can run into that possibility where we're using most of the motor at 60 hertz. And if we try to go beyond that, we don't have enough motor. This can result in a trip. So again, there's a possibility of running trans-synchronous speeds, meaning above 60 hertz, but it depends on the operating conditions. So the higher the pressures that we're operating the compressor at, the further limitations may be applied. Okay, so in this case, if you want to run high speed, very commonly you're going to end up going to the motor 1 version instead of the motor 2. Particularly in medium temp systems. Generally with low temp systems, you can get away with running a higher speed. In fact, that's done very regularly in supermarkets. Okay, and then this is an envelope that actually shows, this is when you select the vary step in the software, and then you look at the limits area. It shows this envelope, and you can see the speed limitations here. So in this particular case, the speed is it's limited to 60 hertz here, but as the pressure ratio gets lower, we can speed it up even more, because lower compression ratio means less work. So that means you have more available motor power, so we can operate at a higher speed. Minimum superheat requirements. Okay, so here's of course, a compressor that's operating definitely nowhere close to the to the minimum allowable superheat requirements. You can see the crankcase here is actually frozen up. Everything's frozen up. On a 2-stage compressor, which is what this is, it's very normal to see heads that are frosting. It's a very low temperature system. It's very normal. It's direct suction, so it doesn't go through the motor first. But you never would see this. A frozen crankcase, frozen motor barrel, and discharge superheats are going to be very low. Lubrication will be very, very much compromised. Some things that happen with as a result of low superheat are wet compression, which reduces evaporator capacity, because what's leaving your evaporator, you've got droplets of liquid that haven't absorbed the heat. So there's heat that could have been absorbed by the refrigerant that wasn't. So that basically enters the compressor, working to reduce the viscosity of the oil. And also discharge temperatures are going to be lower, again, creating problems for the lubrication system. So superheat, the setting of superheat at evaporators is very important. Should always be set so that you can hold a very stable superheat. And sometimes it's necessary to operate at a higher superheat in order to get a stable superheat. Liquid flooding is another possibility. If you've got lots of liquid coming back to the compressor, the first thing that happens is your compressor is being flooded with liquid. So in a semi-hermetic single-stage compressor, this liquid basically comes back to the compressor, enters the motor barrel. And also within the lubrication circuit as well, there's an ejector used in the conventional type reciprocating compressors, which will actually work to pull that liquid back into the crankcase, which we don't want to do. So again, we want to make sure we've got superheat there and enough of it. With the octagon type compressors, there is the partition between the crankcase and the motor barrel is not a complete partition. So for all intents and purposes, they're a common area. So liquid free draining back to the compressor ends up in the motor barrel, also ends up in the crankcase, and also will likely end up in the cylinders. When it ends up in the cylinders, this results in liquid slugging. So liquid slugging is when your pistons are trying to compress something that can't be compressed. So, liquid refrigerant and or oil can't be compressed inside the compressor. So the result of this will be damaged valve plates, damaged valve plate reeds, discharge or suction. Could be a blown web, as you can see here. And when they blow, of course, they would blow from the discharge side into a low pressure area of the compressor. And what's happening here is you're trying to compress something that can't be compressed, and the weakest area is going to blow through in terms of the gasket. And just a note about this, sometimes these webs will blow out because somebody's actually changed valve plates, gaskets, but didn't correctly torque the heads down. Okay, so there is a torque spec for every compressor. For example, the Bitzer CE4s, all of the conventional 4-cylinder and the conventional 6-cylinder all use an M10 type metric bolt with a bolt quality of 10.9, and these should be torqued down to 80 Newton meters or 59, call it 60 foot-pounds. Okay, but it does depend on the bolt size, the quality, and the whole bit. So this isn't information we have to try and remember. You can find this in the technical literature for or operating instructions as well. Actually, it's not in there. It is in technical literature. There's a guide that's actually specifically for torque ratings. So it'll cover all gaskets, even joints that don't have gaskets. It might have O-rings. And again, like I said, bolt size, bolt quality. You can refer to the torque guide for a compressor, and it'll give you the correct torque. So we never want to guess with that. And with torquing, of course, you would always do that in steps. So you do all the bolts down, a certain level, part of the way. You want to go at least 2 steps. I prefer going 3, even if possible. Refrigerant dilution of the oil, which I've already mentioned, reduces viscosity, leads to insufficient lubrication. And as you can see here, this tends to result in if you don't have such a large amount of liquid coming back, or maybe no liquid, maybe it's just refrigerant that has a very low superheat. This even vapor has the effect of diluting the oil down if there's not enough superheat there. So your discharge superheat's too low due to low suction superheat. You'll see this kind of thing where the bearings actually fail. And in this case, you can see where the aluminum is worn. It's like you look at the journals on the crankshaft, which is a special grade of steel, and you'll see what appears to be smeared or aluminum from the connecting rod smeared onto the crankshaft. That'd be a bottom end failure. So if you open up a compressor and you see this, but your valve plates and gaskets are good, that'll be a lubrication problem running low superheats. This sort of thing up here, broken reed valves and what have you, is generally the result of operating the compressor outside the envelope, high compression ratios, and more commonly, I would say, liquid slugging. As I mentioned before, we want to check for adequate and stable superheat at the evaporator outlet. Very important. Becomes even more important, I would say, with CO2 systems. Anyone who attended our CO2 presentations, the webinars that we did with HRAI a little while back, we talked about this also. And with CO2, it takes more of a pressure drop in the suction line to help flash off liquid, but at the same time, the latent heat of CO2 is quite high. It's quite a bit higher than HFCs. So in this case, there's really not a lot working for us in terms of getting rid of that droplet of liquid after it leaves the evaporator. So it's absolutely essential that the superheat is formed in the evaporator and enough of it to ensure that we've got good, stable operation, good evaporator control, and of course, protecting the compressor at the same time. So the minimum return gas superheat is 10 degrees Rankine, but that's just a starting point. Okay, so 10 degrees Rankine, but there's a caveat there. We have to make sure that the discharge superheat also reaches its minimum. And if we cannot achieve the minimum discharge superheat, then we have to increase this value of 10 Rankine or 5.6 degree Kelvin to a higher value to get us to the point where we can achieve the minimum discharge superheat. And you may be wondering, well, how do I determine that? Well, this is easy to do. When you go into the software and you're selecting a compressor, you can try increasing your return gas temperatures or return gas superheat, and you'll see that the discharge temperature will follow. It will increase as you increase the suction gas temperature. Now, in some cases, a good example of this would be a close coupled system. it may be impossible to get that higher amount of superheat. And, to increase the superheat using the expansion valve alone can be very inefficient once you get above, 10, 12 degrees, depending on the application. In this case, a liquid to suction heat exchanger can come in very handy, very useful, help boost up the efficiency and the reliability and the availability of the compressor. Okay, so these minimum discharge superheats are refrigerant dependent. Most of your HFC and HFC HFO blends require 20 Kelvin, 36 Rankine. With some of the other refrigerants, 30 Kelvin or 54 Rankine is required at the discharge. In order to prevent a compressor from operating at an excessively high suction pressure, we need to have a way of limiting the suction pressure. So by understanding what the limits are of the compressor, we can use this information to determine how we need to set these pressure limiting devices. Of course, when you start a compressor, it's quite likely, especially for a first-time startup, that the compressor has to start outside the envelope and then eventually will be pulled inside the envelope. So this is very normal and acceptable, but it's very important to understand that the operation within the envelope must be achieved within a 2-minute period and preferably less. And if we can't achieve that, this is an indication that we need to have some kind of pressure regulating devices on there of some sort, because allowing the suction pressure to operate at a very high level for extended periods of time is possibly going to create damage to that compressor. Okay, and also when you're operating very high suction pressures, it follows that at high suction pressures, your saturated, your discharge pressures are going to end up being higher as well. And there may not be enough condenser surface available on the system to reject all the heat, making things very complicated for the compressor and reducing the life of the compressor. So during startup, it's very important that we observe the pressures and temperatures during pull down. So we're looking at actual pressures and comparing them to the limits, and also the minimum allowable superheats entering and leaving the compressor. And anyone who's heard me present at other seminars and that sort of thing knows that I talk about discharge superheat a lot, and it doesn't seem to be commonly looked at. And one comment I get in the field is that, we've never heard of discharge superheat. Why are we looking at discharge superheat now? And this is something actually that I learned many years ago when I came on board with Bitzer, that discharge superheat is very important. And it just makes sense because the overall superheat in the discharge is going to be a function of a few things. It's going to be a function of compression ratio, the type of refrigerant you're using, and your return gas superheat. And as it turns out, the discharge superheat is what we're using to determine if we have enough separation of the refrigerant from the oil to ensure that we have sufficient lubrication of the compressor. So a crankcase pressure regulator valve is one way in which to limit the suction pressure entering the compressor. So the crankcase pressure regulating valve, or CPR valve, is adjusted to prevent compressor overloading. And some are inclined to set these regulators based on amperage. I don't really recommend that because that amperage can change as your condensing temperature varies as well, and your saturated discharge temp. So as the discharge pressure varies, amperage is going to vary even if you're holding a certain suction pressure. So the best way to do it is set the maximum outlet pressure of this valve. This will be the outlet. There's an arrow here. I don't know if you can see it. This will be the outlet. So this is the compressor side. This is the evaporator side here. You would set this valve to achieve an outlet that doesn't exceed the maximum operating saturated suction temperature of the compressor, or even lower, depending on what the case may be, what you're looking for. So that also limits load on condenser. Like I said, if the suction pressure entering the compressor is lower, it follows that the load on the condenser is going to be lower as well. The discharge pressure is going to be lower, reduces the stress on the reed valve. So some of the things that we'll see happen to reed valves when they're becoming stressed due to very high pressures and rapid oscillation due to high mass flow rates, what have you, will be basically hammering of these valves where they drop into the cylinder, and then they rest against the suction seat, which is just supported by a machined out portion of the cylinder wall, which allows this suction reed to sit in it. So we're looking at the bottom of the valve plate here. So over time, these can actually experience so much oscillation and hard work and stress that those tips can actually break off. An electronic expansion valve is another way of doing it. And yes, you can have pressure limiting with thermostatic expansion valves as well. But with the electronic expansion valve, you have the benefit of being able to adjust this. You can also adjust other things such as the percent opening and how much it should be open during startup for a certain period of time, that sort of thing. So this is another way that we can limit suction pressure to a compressor. One of the other benefits, of course, with a valve such as that is that you can get, it's expected that you can get a quicker response time due to a smaller sensor. So when you have a smaller sensor, the sensor can change, the temperature of the sensor can change more quickly. Whereas if you got a great big bulb on an expansion valve, that tends to take a little longer to warm up and cool down as the refrigerant flow varies through the expansion valve. Discharge temperature is another topic. So checking the discharge temperature is very important during startup, but also, throughout the life of the compressor, it's always a good idea to take a look at discharge temperature during maintenance. And when you do this, I recommend using a good quality meter, of course, fairly accurate and repeatable type meter, using a good surface probe, and just be aware what the limits for the compressor and refrigerant are, and generally they're published in the literature. And you would check by locating the discharge line, and you would put your sensor 3 to 4 inches or so at the most of the discharge service valve. So the idea is to get as close to the compressor as we can and get a good temperature reading. High discharge temps are usually due to high return gas superheats, the absence of auxiliary cooling, for example, a head cooling fan, refrigerant injection. Operating at high compression ratios, as I mentioned before, will also contribute to high discharge temperatures. Throughout the life of a compressor, as a compressor wears, discharge temperature will increase as well. So if you have a system where you have 2 or more compressors on them, and they're all exposed to the same suction and discharge pressure, but you see one is operating at quite a high discharge temperature, it's very likely that compressor is worn inside, or something's broken. That could be a web on one of the gasket webs, reed valves, something like that. But it indicates there is something wrong with that compressor. So for additional cooling, of course, you can use a head cooling fan. And historically, a head cooling fan would be energized using a normally open auxiliary contact on your compressor contactor. So when your compressor contactor closes, so does the auxiliary contact on the switch that's physically mounted to the contactor. It closes and therefore brings the head cooling fan on. So it wasn't really temperature controlled. You would just run the head cooling fan as long as the compressor is running. And you could, in theory, have a temperature sensor there, and you can control it that way as well. But that's not typically, at least here in areas where I've seen equipment operating. Generally, it has been auxiliary contact used to do that, or even sometimes just a control relay. They'll use that to energize the head cooling fan. So an alternate and even better way to do this is, with the newer type controls, for example, the IQ module in this case will cycle the head cooling fan. And the neat thing about this is it's only going to operate the head cooling fan when it needs to. So that compressor could start up and run, and the head cooling fan will not run. So when it's cooler outside, low compression ratios, that head cooling fan may not run. And then when it gets really warm outside, for example, on an outdoor air cooled system, then the IQ module may start cycling that fan, and it will cut in at 248 degrees Fahrenheit and cut out at 212 degrees Fahrenheit. Once that fan is on, it'll run for a minimum of 300 seconds. Okay. So here, unloading, if you're unloading more than 50% on a 4-cylinder or 33% on 6 cylinders, then that head cooling fan will be on by default as well. So refrigerant injection for situations where the head cooling fan is just not enough, refrigerant injection is recommended, and refrigerant injection should be done with the IQ module. The IQ module has an algorithm built in for the injection of refrigerant to cool the compressor, but doing it safely. We're talking about minimizing, or limiting our return gas superheats and discharge superheats, discharge temperatures in order to prevent overheating of the compressor. But the flip side is we don't want to have too much refrigerant going into that compressor that it starts diluting the oil and creating other problems, reducing the life of the compressor. So the algorithm here will cycle, and you'll note these values are quite high. The refrigerant injection solenoid will turn on at 275 degrees Fahrenheit. And in this case, it'll actually cycle that solenoid. But if it does reach 284 degrees, which is 140 degrees Celsius, then the injection will be continuous. And this isn't a full stream. It's more or less an atomized stream that has to pass through an orifice. So the orifice will depend on the compressor body size and displacement as to how much refrigerant is actually going to be injected in there. And as the note implies, if you do a search for HRAI, Bitzer IQ, that'll take you back to the IQ module presentation. Discharge temperature monitoring. So we know that compressors can overheat. And in this case, it's a really good idea to have discharge temperature protection on there. Anytime a head cooling fan is used, I recommend using a discharge temperature sensor. I also recommend using it whenever you're unloading, because if unloaders are set such that the compressor can overheat, the discharge temperature is going to increase to a point possibly that will cause the compressor to trip. And when that happens, we can safely shut the compressor off without overheating it and carbonizing the oil and everything else. So with the IQ module, the discharge temperature sensor is included by default on all packages. So if you're applying a compressor and you're not using the IQ module, for example, then you would, I recommend using the high discharge temperature sensor whenever possible. Even if you don't have auxiliary cooling, it has benefits. Like I said, with unloading, but if you got a compressor that's wearing over time, the discharge temperature sensor is going to give you more information about the operation of that compressor. And for the cost of a discharge sensor compared to a compressor, frankly, I think it's a good option, a good accessory to add. So these discharge temperature sensors simply wire in series with the motor sensing circuit on the protection module itself. The newer modules, by the way, for reciprocating compressors are referred to as an SE-B5. In the past, they were SEB1s and 2s and 3s. Well, under EN, this is a European requirement, and then UL 60730, there's an additional requirement to protect against short circuit monitoring of the sensing circuit. So if you're familiar with these modules, they generally have 2 orange wires on them that would connect down to your motor sensing circuit inside the compressor, okay, inside the semi-hermetic compressor. In the past, you could take those 2 orange wires and you could jumper them together, and you can power up your module to test to see if the module is allowing the compressor to come on. So you would check between terminals 11 and 14, and if they close, then you know the module is working. But of course, with this new method, this can only be done using a resistor. So you'd want to use some kind of resistor that's perhaps 300 to 1,000 ohms or something like that across the orange wires. So this is a newer requirement, and this is why the modules have been recently replaced. Overload protection with safety lockout. Like I said, the modules will protect the motor in a sense that they'll prevent it from overheating. But more importantly, the main reason why the module exists is to meet code. So a compressor that actually has a nameplate on the side that says thermally protected is a compressor that has a module with temperature sensors that are embedded in the windings. They're actually, you can't replace them. They're inside the motor windings, and everything is varnished over. There's one sensor per motor winding. So if it's got 3 windings in the compressor, it'll have 3. For the larger compressors, they'll have like the 6 lead compressors, for example, and the 9 lead compressors, they all have 6 windings in them. And when you have 6 windings, you've got 6 windings that have each their own sensor inside. Okay, and then they're all connected in series back to the module. So like I said, the discharge temperature sensor will be wired in series with the motor PTC sensors. So now either a very hot motor winding temperature sensor or a discharge temperature sensor could take that compressor offline. And you may be thinking that the resistance is getting shifted all the time every time you add a sensor, and that's true. But that's the benefit of using a PTC type sensor, is that we don't see a lot of change in resistance as the temperature increases until it gets to a certain value. And then it's going to really elevate quickly, depending on the characteristics of the sensor. And this is why you can do it. Generally, you can put, I think, up to 9 sensors in series using this approach if you needed to. But in the case of the Bitzer compressors, generally 6, 7 sensors in series is enough to cover everything. High discharge temperature, again, can be a result of high return gas temperature or return gas superheat. This results in higher suction volume of the suction vapor coming back, okay, because as you heat up a gas more and more, the volume or the specific volume of it increases, can result in less motor cooling. Semi-hermetic compressors use a refrigerant-cooled motor. Therefore, we have to have a sufficient amount of refrigerant coming back to cool the motor. And at the higher compression ratios, this can result in an increase in re-expansion of gases, which re-expansion of gases basically just further increases discharge temperature and reduces flow. High discharge temperatures can also be the result of the absence of auxiliary cooling. So the head cooling fan maybe was installed, but it's not working. But if we have a discharge temperature sensor on there, now we have something to shut that compressor off instead of allowing it to run and burn up that oil. Same thing with liquid injection. If something happens with the liquid injection, an orifice plugs up due to a dirty system or something like that, a discharge temperature sensor would take that. In the case of liquid injection, will be the IQ module. Then the IQ module can safely take the compressor offline before it overheats too much and creates a problem for the compressor and also for the oil. A damaged or worn compressor, as I mentioned before, can result in high discharge temperatures as well. So this is just a drawing that shows, like I said before, you just take your discharge temperature sensor, wire it in series with your motor PTC sensors, and now you've got protection of you got a module that's looking at motor temperature and also your discharge temperature. Note with the newer approach to the enhanced compressor technology, now with the IQ module, the discharge temperature is actually increased to 150 degrees C or 302 degrees Fahrenheit, which is a little more than what it was before. But basically what's going on here is the IQ module coordinates the operation of the various compressor accessories. Anyone who watched the IQ module video may recall that the accessories on the compressor, head cooling fan, refrigerant injection, crankcase heater, unloaders, and that are all controlled by the IQ module. So it's all coordinated by the IQ module. So the allowable discharge temperature is a little bit higher when you're using the IQ module in that application. In the future, by the way, the IQ module will become standard equipment. It'll be more of a basic version of the IQ module, and then there'll be like an add-on module depending on the application. If it's a supermarket rack system, for example, if it's a condensing unit or what have you. So there'll be different options. It'll be basically a CMRC2. So the second version of the control module for reciprocating compressors, CMRC, and that will be the case at some point in the future. In addition to that, envelope monitoring, if you use the pressure transducer kit, which is an option, and then you program in the compressor model number and you program in the refrigerant type, then the module loads the envelope for that particular compressor. And if it has the ability to sense the pressures, then it can ensure that the compressor is operating within the envelope. And it can coordinate the accessories to do that. And if it starts going outside the envelope because something's wrong, then in that case, then the IQ module will take the compressor offline. So there you go, Matthew. It's I think it's about 10 to 1. So we have a little bit of time for questions, fortunately.
Good timing as always. Thank you so much, Phil.
My pleasure.
Definitely a lot of good information. And if you'd like to go over it again, obviously Phil's happy to answer your questions at his email down there, or the webinar is available on our YouTube page. But we do have 2 questions. So let's start, both from Anonymous. First one goes, how does, I'm just going to move it to this screen so we can see it better. Here we go. How does low discharge superheating result in higher oil carryover? In brackets, lower temperature should be causing higher viscosity? Question mark.
Or yeah, the lower discharge superheat can actually result in less lubrication. If you think about reciprocating compressors, as with other compressors, there's always some oil in circulation in the system. So we want to minimize the amount of oil in circulation. If you think about just imagine the amount of time that refrigerant and oil mixture are actually in the compressor by the time they enter the compressor suction and leave the compressor discharge at a speed of 1750 RPM. It's not in there very long. And the problem is the refrigerant, when it comes into the compressor, there's always this interaction with the oil. It's exposed to the oil, or the oil's exposed to the refrigerant. And when you're running low superheats at the suction, then the oil will absorb more and more refrigerant, reducing its viscosity, reducing pump pressure. And this is something you can see if you put pressure gauges on an oil pump on the compressor. If you're running low superheat, you may have low oil pressure, and then you increase that superheat, you can see the oil pressure increasing as well. It's the other side of it is that with the higher compression ratio, your temperature is going to go up, and discharge superheat tends to go up automatically for a given suction superheat. So this is just a way that we evaluate. So we'll pick a limit such as 36 degree Rankine, 30 degree Rankine, 54 degree. I had that number wrong too. It'd be like 20 degree, 30 degree Kelvin actually. And for 30 degree Kelvin, your minimum discharge superheat would be 54 degree Rankine. And for 20 degree Kelvin minimum discharge superheat for a lot of your HFC, HFO type refrigerants, that would correspond to, so 20 Kelvin would be 36 degree Rankine. It's just a way of us knowing what the result of the compression process is. Discharge superheat is a very good way to determine if you have not only superheat entering the compressor, but do you have enough? Okay, so I hope that makes sense and clears that up.
Thank you so much. A few more questions for you. What is the difference between liquid flooding and liquid slugging?
Liquid flooding is basically liquid draining down the suction line and entering the compressor is flooding. And then, that liquid can then enter your lubrication system and create problems with it directly. Slugging is when that liquid actually enters the cylinders and then the piston tries to compress that in the cylinder. Okay, so that would be liquid slugging. And liquid slugging, as I said before, can result in damaged valve plates and or blown gaskets on the valve plate.
Thank you. Will the CMRC upgrade be available aftermarket?
Yeah, the CMRC 2, I believe it will be. As I mentioned before, it will be standard at some point in the future. It'll become standard equipment, and then there'll be an add-on module. The CMRC 1 was available as a retrofit, and also in new applications. I believe that that's also the case with the CMRC 02.
Excellent. Rapid fire. How does unloading cause overheating or overheat?
So when we unload a compressor, if you imagine a compressor running, let's say it's a 6-cylinder compressor, medium temp application, for example, when you unload by one step, you're unloading one head, which is two cylinders. You're reducing your flow by approximately 33.33%, by exactly 33.33%. And then if we that reduces the mass flow accordingly. So the refrigerant flow rate through the compressor. If we were to unload the next unloader at the same time, so now we've unloaded the compressor by 66 and 2/3 percent, then we have even less flow going through the compressor. And as we have less flow, we still have a certain amount of motor heat. And yes, the load on the motor is dropping as you unload, but the motor itself requires a certain amount of energy even just to maintain a magnetic field. And we always have to get rid of that heat. So if we don't have enough cooling of the motor, then the discharge temperature is going to increase. And when you unload a compressor, especially too much, then the flow rate gets so low that we just don't have enough cooling for the motor inside. Okay,
Final question. Oh, I'm sorry.
No, that's fine. Sorry.
Final question, more of a comment. Thank you very much for the webinar. Lots of good information that comes from Anonymous. But I would tend to agree with that statement. A lot of good information, Phil.
My pleasure as always. Thanks for the opportunity once again.
Yeah, you know what? I'll be reaching out to you soon to book something for fall. So just keep those
Why
emails
not?
open. Look, we got 2 more minutes, so I think we're gonna put a pin in it. If you'd like to watch this again, as I said, HRAI YouTube page, but also on the HRAI page, you can go, you can contact us and set up your own webinar for HRAI members as well. And you can be like Phil in the top corner there, being a star and giving some good information to members. Reach out if you'd like to do that. Otherwise, thank you once again, Bitzer, Phil, and we hope to see you again.
Thank you very much. Look forward to it.
Have a great afternoon, guys.